MacBook, which is irritating me, but whatever. I can see the chat. All right, everybody, here we go. We're going to do some review of Chapter 10, and these are just some practice problems that I came up with. So let's see here. We're going to start with the first one, question number 1. It says, in the molecule shown below, determine which of the highlighted carbon-hydrogen bonds, there's 5 of them, which one is expected to have the lowest bond dissociation energy. So what that means is if we were to break the bond, we would end up forming the most stable radical. So could anybody identify that proton? Which one would, if you broke the bond, you would end up, or which one would have the lowest bond dissociation energy? Which one of these bonds would be the easiest one to break? Well, the first thing I noticed is that it can't be E and it can't be D, right? Because those ones are vinylic. Yeah, I see somebody put their correct answer already. These two are vinylic, so it's definitely not those. Yes, and my students clearly identified that it's this one here. It's HC, because not only is it tertiary, but it's tertiary allylic, right? So if you were to break that bond, you would end up with a radical that is resonance stabilized. And HA and HB, neither of those would produce anything particularly more stable than a tertiary allylic. HB would be tertiary, HA would be secondary, but again, tertiary allylic would be the winner there. All right, let's move on to the next one, number 2. It says rank the following radicals in order of decreasing stability. So we'll go from most stable to least stable. So we'll write it down like this. We'll put most stable over here, and then we'll put least stable down here. Let's go with the least stable first. Is there anyone here that just, you think might be the least stable of all? It's going to be everybody answered that right away. It's the 4th one, isn't it, right? It's the 4th one because it's primary. So number 4 is going to be the least stable. Is there anyone that anybody identified as the most stable? Yeah, definitely. Yeah, all my students nailed that one, right? They all said number 3. And the reason why is because it's tertiary allylic. Now, if you look at number 2, it is allylic, but it's only secondary allylic, so that's not as stable as tertiary. So this one is secondary allylic. So number 2 is going to be next. And then number 1 is secondary, but it's not resonance stabilized. Or sorry, number 1 is not resonance stabilized, but it's secondary. So there you go. So we've ranked all of them. I can bring this information over maybe a little closer like that. There we go. All right. So we were able to rank these radicals in terms of their stability, going from the most stable being number 3, which is tertiary allylic, all the way down to number 4, which is just primary. All right. Let's try. This is kind of a repeat of question number 1. It's the exact same question. Which one of these carbon-hydrogen bonds is going to be the weakest? So, yeah, anybody have a feeling about this one? I see a couple of bonds that are of interest here. Would it be A, B, C, D, or E? Yeah, I see somebody says, yeah, we get some ideas going here. All right. So if we were to break the bond where we have HE, so if we were to break that bond, so let's do HE, that would give us something that looks like this. So we would have something that is secondary allylic. Oops. We still have our methyl group over here. And then here we have an isopropyl group like this. All right. So now that you see that radical, is there another proton that you think might produce something even more stable than that? What if we were to rip off HD? Right? If we were to pull off HD, then we end up with something that looks like this. So, oops, there we go. So we end up with a radical as well. But the difference is that this radical is tertiary allylic. All right, and this one is allylic, but it's secondary allylic. And so the winner is going to be the tertiary allylic. And so the winner will be this one here. Give me a thumbs up if that makes sense now that you've taken a look at both of those radicals. Sure. Okay, great. Yeah, absolutely. And then HA is also allylic, right? There's HA, but it's primary allylic. So the tertiary allylic would be the winner there. All right. Let's take a look at number 4. Which term most accurately describes the process shown below? So we have a bromine radical, and then we have propane, and then we end up with HBr, and we end up with a propane radical. So is this a coupling? Well, coupling, it can't be that, because coupling is where you annihilate two radicals. It's not a proton transfer because that's an ionic mechanism. Then we have halogen abstraction, hydrogen abstraction, homolytic cleavage. Well, we can definitely eliminate homolytic cleavage, because homolytic cleavage is where you start with no radicals and you make a radical. So it's either a hydrogen or a halogen abstraction. Anybody have an idea which one of these it is? And then we could practice the mechanism maybe. Which one would this be? Are we abstracting a halogen or a hydrogen from the propane? Right, we're pulling off a hydrogen, aren't we? So this is hydrogen abstraction, right? So we could pencil in, we could just scribble in a hydrogen atom like this. Of course, there's two of them there, but we're just going to put in one. And what's going to happen is we're going to make a bond between the hydrogen and the bromine, and then we're going to form a propane radical like that. So this is a hydrogen abstraction. It is not a halogen abstraction. There we go. All right, next question. Which term most accurately describes the process below? So we have a bromine radical, and then we have a double bond, and we're ending up with another alkyl halide that is the radical. So is it a coupling? No, it's definitely not a coupling, because like I said, a coupling is where you annihilate two radicals. Is it a hydrogen abstraction? Well, we're not removing any atoms from the alkene, so it's not that. We're not removing any halogens. Is it a homolytic cleavage? No, because homolytic cleavage is where we take a non-radical and make a radical. It's in addition to a pi bond, isn't it? Right, and you could practice drawing the mechanism for this. Right, we're forming a bond between the carbon in the center, if you will, and the bromine, and then we're making this tertiary radical like that. Give me a thumbs up if you're with me on that one. Addition to a pi bond. All right, cool. And don't hesitate to stop me if you have any questions. Let's keep moving along. All right, so now we're on to question 6. Oh boy, it's a long one here. It says, which of the following is an example of termination? Well, remember we have initiation, propagation, and termination. And termination is when you have two radicals. I'll just draw two R groups, coming together, and then you annihilate the radicals, right? So you end up, forming a sigma bond, and then you have no radicals at the end. So which one of these looks like the best answer? It's not a trick question, I don't think. So termination, it would be C, right? C is the one where we have two radicals. We're adding a propane radical and a bromine radical, and we're ending up with two bromopropane, and then we have no radical.